Can I just go? Very good. Now, still good morning. So we're going to do something very different to what you were doing before, and I hope you're okay with it. They asked me to participate in this, and I gave a few topics. And but this is what I like to do. So try to explain. In fact, what I would like to do is try to explain to you how to design a SAR mission, which is way too ambitious for. It's okay. Which is way too ambitious for a session. But I want to give you a bit of a feeling of what goes into the specification of a SAR system and what are the trade-offs. But we have very little time, so I have to run. And to do that, I have to explain a bit how a SAR system works. So I'm trying to blend a bit the basics of a SAR system, what it does with what it means in terms of specifying the SAR system. So it's very different from a talking about how you work with data. It's something very different. This is a slide from ESA, which I like, and I always try to use it as often as I can, because it shows the landscape of Earth observation missions by ESA. And there is also Earth observation missions in Europe, not by ESA, and outside Europe there are also people doing stuff. But this is what we are doing in the ESA context. And what I always try to show people is that most of the satellites that are in the planning are really in the planning. They are coming. And this is why it's good for you to be here, because there is lots of work to be done in the future. And there was a lot of work done in the past, but there is much more coming up in the future than what we have done in the past. So most satellites that we think of are coming, and we continue adding things to them. And then there is one circle too much. Now I'm pointing to my personal satellites. So I have a slide later where I will show them a bit bigger, but these are my personal ones. And then there is one circle too much, but these are SAR systems in the landscape. So there are many SAR systems. They're an essential part of our Earth observation system for many reasons. And in fact, we're getting more of them. Also commercially, we're getting many of them, but also ESA is expanding the amount of SAR satellites we have. So they are an important tool for many reasons. And that's why it makes sense to talk about them and understand a bit better what they do. I'm going to zoom into a category of the satellites, Earth observation satellites that we have in Europe in the context of ESA, which are the Earth explorers. And I show you the slide basically because I like it. And these are the Earth explorers. Harmony, again, my satellites. This is the 10th Earth explorer, and there were 9 before. And in this collection, there are 2 SAR systems, so the Harmonies and biomass. And in fact, even Cryosat was doing some synthetic aperture, but we can forget about that. But you see, even here, as scientific missions, 2 SAR systems, and just to illustrate that they are very important. And I thought I would start really to motivate you by showing you a picture, a SAR picture from biomass. And biomass is very special for me, because I was working on it a lot 10 years ago, 11 years ago, before it got selected. So I put a lot of effort, and then when it got selected, I was still putting some effort, and then I lost contact with it. And then about 10 years after I lost contact with it, it got launched. So biomass was launched this year, and it's producing beautiful images. And it's really a nice case study of what a SAR system can do for you, because it's very different to what other sensors can do for you. So it's an imaging system, but it's not looking at the surface. It's actually penetrating. It's looking under the canopy, and which allows you to do things that you could never do with optical systems or other things. So it's a nice example. So I thought let's celebrate that it's there. We can zoom in a bit, and then and you can see, so biomass was designed to look at biomass. It will do many things better than estimating biomass. But the reason why you can estimate biomass with the biomass mission is because it's actually integrating the return from the entire canopy under the trees, from the ground of the trees all the way down to the ground, because the radar waves are penetrating through the canopy. And so you're getting return from the integrated forest. And if you were to design a mission like this, back then they had to make choices, and one of the choices that they had to make was what frequency do we use? And also, if you design optical systems, you have to choose what wavelength. Radar people think in terms of frequency, not wavelength, but it's the same. And in that case, they wanted to penetrate a lot. And if you want to penetrate a lot, you want long wavelengths. Short wavelengths will bounce at the first obstacle and stop propagating. Long wavelengths will propagate. So that would be one of the choices that you have to make. So if you are thinking of a satellite mission with a radar, the first question I'm going to ask you is, what frequency do you want? And there the question is, do you want to make a cool imaging system with very high resolution to see things on the surface? Then you go to short wavelengths. Or do you want to actually have a really interesting radar system that does everything a radar can do, which is penetrating through semi-transparent media, and then you go to longer wavelengths. So that's one of the choices that you would have to make. This is just a picture, because I like to have this picture in every talk I give these days. These are, I told you, my satellites. This will be launched in 29. And it's a bit the extreme case of what you can do with the SAR system when you start adding satellites and you don't have just one, but add several receivers. I would love to give a talk only about this, but I'm not doing it today. But anyway, this was just to make myself happy. Contents of the rest of the presentation is this, but you will see it, and I will not waste some time. So I'm going to start directly with trying to introduce the basic concepts. I already introduced one. Then SAR systems are cool, radars are nice, wavelength matters. The other thing I want to tell you is that radar is actually an acronym. Now people use radar in the totally wrong way for many things, and they talk about optical radars and things like this, and they are not radars, because radar means radio detection and ranging. It's an acronym, and when we do synthetic aperture radar, we're putting an acronym inside an acronym, because we do synthetic aperture radar and we call it SAR. But it has a meaning. You know this probably. Radars are active. SAR systems are active. That means that I find it very funny when some colleagues working with optical systems and looking at the polar regions are very happy when the sun comes up, because for half a year they can look at their target of interest. And we radar people can always look at the target of interest. And that's because we carry our own illuminator. I told you microwave frequencies, so wavelengths are somewhere between this and this, so very long wavelengths, which means that what we see is very different. We penetrate through media. That can be good or bad. So if you want to measure the height of something, you do not want to penetrate, because you want to really measure the height of something. But if you want to integrate biomass, then you want to penetrate through it. If you want to look at the structure of ice and snow, then it's nice that you can penetrate through it, because you are not seeing the surface, you are seeing under the surface. This is what, if you read any paper on SAR, chances are high that it will start by telling you that we can look through clouds and day and night. The clouds thing is an important thing, because if you there is about 70% of the time the Earth's surface is covered by clouds, which is the other problem that optical people have. It's either night or it's cloudy. We radar people do not have a big problem with clouds. It's not true that we are that we don't see anything. So clouds, you can sometimes see it. If it rains enough, we see it, but mostly not. Now, the difficulty, if you work like me for all your career on radar, with radar images, then you look at the radar image and you think it's wonderful. If you don't and look for the first time at the radar image, you don't understand anything. And the reason is because we are used to looking at optical images. We have an optical system in our head. So we're used to look and interpret optical images all the time. We are not used to interpret radar images all the time. And the kind of image we get is more difficult, therefore more difficult to interpret. And one should always remember that the radar image is not a picture. And some people try to fuse optical and radar. And typically what you see is people trying to fill the gap caused by clouds at night by putting a radar image. And you can do that, but that's not really what you want to do. You want to treat a radar image as a totally different beast with different information content and exploit that information content. It's not a replacement for an optical thing when the optical thing is not working. It's a different measurement that you should exploit in a different way. And ideally, you can combine different assets by exploiting the different information content. An important one, and part of the reason why I wanted to give this talk, is that the performance of a radar system is fundamentally constrained by physics. And that applies also to an optical system, of course. But because we have this very long wavelength, our constraints are much harder. And when people think of satellites and putting systems on a satellite, people imagine that with enough technology, you can make everything smaller, right? You imagine that now we have very big cameras in space but maybe in 10 years, they will be very small and we can afford very small satellites with very small little cameras making great pictures. That's not true. Even for optical systems, that's not true. And there are physical constraints in how small you can go. But for a radar system, the constraints are very, very hard. So you're never going to have miniature CubeSat SAR systems providing you beautiful images because it just cannot be done. And you can actually calculate the fundamental limitations and see that you need a big machine with big solar panels, with big batteries, and generating a lot of power and receiving a lot of signal. And even then, things like resolution are constrained. So you can make movies where you can read the plate of a car from space, or maybe read what somebody's writing from space, and that's not totally absurd. But if somebody makes a movie reading a plate from space with a SAR system, that's not going to happen because you cannot go that high resolution. So you cannot expect this. And the other thing that I think is important, and conceptually very important, is the fact that that radars are coherent. And coherence seems like a good word, but it's actually not in the context of imaging for most purposes. Sometimes it's very nice, but sometimes, often it's not. When you make a picture with your camera, you are actually averaging over time. And every nanosecond, you get a different realization of the image. And you integrate, which means you average. And by averaging, you improve the quality of the image. And if you do photography, you know that at night, you just let the aperture be longer in time, or you open the aperture, you get more photos, you integrate more, and you can get a nice image. The radars, they make repeatable images. So if I'm here, I put a radar, make a measurement, and I repeat it after a second, I get the same measurement. And I can repeat it over and over. Then, except for the noise introduced by the system, most of the thing I do is repeatable. I get every time the same. That's not nice, because the reason why a picture is nice is because you have averaged the randomness of the image out. And when you do the same with a radar, you don't average anything. You get the same thing over and over. Now, this is great if you want to look at change. So if I measure today and I know that tomorrow when I measure again, I'm going to look at the same thing again, that's nice, because if I see a difference, then I know something changed. And this allows me to measure motion, allows me to detect change in a very quick and effective way. But if you really want quality, then you want to average, and radars are bad for averaging. And that's why when we talk about resolution, so if you want to specify a system, any system, so if you want to specify an optical system, a radar system, then one of the things you will need to specify is resolution. If you are doing an optical system and they tell you the resolution is 1 meter, it's clear what you mean. If somebody sells you a SAR system and they tell you the resolution is 1 meter, but the information is not really complete. It depends on what you want to do with it, because you are going to need to average. Then you are going to need to decide how much you average, and when you average, you are going to give up resolution in exchange for quality. So the word resolution in the case of a SAR system is not a simple thing. So we can give you a number and we can tell you some company has a system with a meter resolution, and that's great, but that's not really true, because you need to degrade the resolution in order to get a nice image. Okay, some equations for you. There are more coming, and you should not look at them. The important thing in a radar is that we can position things, because things at different distances produce echoes that arrive at different times. So the people in the back of the room, if I'm the radar and I transmit, their echoes will arrive later. The people in the front, their echoes will arrive first. If I can distinguish when they come, then I also distinguish where you are in distance. Okay, that's the important thing I wanted to say here, and then I will go to resolution. And I had beautiful slides going through a very nice derivation, which I'm skipping. So I'm just going to put this one and then try to explain what we have. If you take any radar, one of the things we care is resolution. We are making 2D images, so we care about resolution in 2 dimensions. In an optical system, all resolution is angular, so the cameras can distinguish direct direction of arrival, so it's an angular thing. For a radar, one dimension is distance, the other one is something else. For distance, you need to be able to discriminate the echoes coming from different targets, and intuitively, that means that you transmit a very short pulse, so you can distinguish things. Now, this is not how it works. We do something more clever than that, but it doesn't matter. At very high level, what matters is the bandwidth. A very short pulse would have a very large bandwidth. If you know Fourier transforms, then you know short in time means large in frequency domain. If you do not know about the frequency domain, you just believe me. If you want high resolution, you need bandwidth. If I'm now in the game of designing or specifying a mission, and you are frustrated because the resolution is not high enough, so you say, yeah, why don't you put more bandwidth? Then I'll tell you, because the bandwidth is constrained in many ways. First, from an engineering point of view, but more fundamentally, from a legal point of view. I cannot claim all the bandwidth because there's people trying to use the same microwave spectrum for communications. There are people trying to do astronomy. There are parts of the spectrum which I cannot use because there is too much absorption in the atmosphere, but it's mostly legal constraints. It's a fight between us, the Earth observation people, and the people doing communications who want to use all the bands for themselves to get more Netflix in 16K TVs. So in the future, you will have this fight. So you will, if you are doing Earth observation with radar, you have to fight for the bandwidth and convince people that you need that one because imaging is important. So more bandwidth, better resolution, and that's a very fundamental thing. C is the speed of light, and 2, in all radar equations, there is always a factor 2 coming from the fact that the signal goes and comes back. And the two-way introduces a factor 2, which leaks in all the equations. Not super interesting, but just for you to know. Okay, so it was the pulse bandwidth, and then I have a slide with the geometry that we have. We are looking at side-looking radars, and they look to the side. You also have radars that look straight down, and that's what you want to do if you want to measure the distance to the Earth, to do altimetry, for example. Imaging radars, they look to the side. And the reason why they look to the side is because that's what creates a mapping between position on the ground and distance to the radar. If I look straight down, everything is at the same distance. If I look a bit towards the horizon, then farther away on the ground means farther away from the satellite. So we look to the side, and this creates imaging capacity in range. And then this gives us a geometry. So we have a swath. So this is the size, the width of the image. In principle, you could make infinitely long images as you fly, but in range, in distance, you are constrained. You're constrained somehow. So I have some angles here, things that you care about. Maybe okay. Now I became a flat earther, so everything is flat. You can do most things simplifying to a flat earth geometry. It works fine. So we have a swath. The closest point is what we call near range. The farthest point is what we call far range. There is a distance, which is this R, which matters. There are some angles. There is what we call the look angle, and as a user, you don't care about that one. As an engineer designing a SAR system, is really what you care about. And then there is another angle, which is the angle of incidence. And in this flat Earth geometry, with no topography, that both angles seem the same. If you go to space, because of the curvature of Earth, at least if you believe the Earth is curved, then these two angles are not the same. And if there are slopes on the ground, then these two angles obviously are not the same. But and these things are things you care about, because depending on the angle of incidence you use, the image is going to look different. So when you are designing a mission, I'm going to ask you, what frequency do you want? Depends on the application. And I'm going to ask you, what angle of incidence do you want? You will not know, so then I will make it up myself. But that's an important choice, and for many reasons, and it's always a trade-off. Okay, so look angle, incident angle, things that you don't care about, so we can go to the next slide. I used to think this was a very important slide. It is, but less I realized later when I learned about other things. So I'm trying to do a 1D projection of a very silly topography into a radar image. And since we distinguish things by their distance, and then there is a projection from whatever is on the surface into the geometry of the radar. And then we can see some things. I'm trying to represent the resolution of the radar, which distinguishes by distance, not by anything else, and how it maps on the ground. And then if you draw it, then you can see that the resolution on the ground is not the same as the resolution in slant range. So slant range is what the radar measures. Ground range is what you care about when you're making an image. And you can see several things. You would, if you think about it, you would see that the resolution for a given bandwidth, for a given spacing in slant, is going to depend on where you are. Right? The farther away you go, the better. In fact, when you go to close range, then you lose resolution because of how think about it, and you will get it. But then you see also some effects, some deformation of your image. And the one I'm showing is for a shortening in the wrong color because PowerPoint looks a bit different. But you see that if I have a slope facing the radar, then I start losing resolution. And if the slope is perpendicular to the line of sight, no resolution. 1 pixel becomes infinitely large, which is not very nice. Here you will see the opposite. So if you have, in the downslope, you have the opposite. And then we have two other effects, which we always try to call. One is layover, which should appear with different letter type. Here, what's happening is that the top of this mountain, and if you look at cities, it's very clear. If you look at the sharp picture of Paris, then you see the Eiffel Tower very nicely. The tip of the mountain, of the tip of the Eiffel Tower, is closer to the radar than other points which are actually closer on the ground. So you get this thing. So things appear like they're laying on the ground. So the Eiffel Tower looks like it's laying on the ground on top of other things, which is not okay. And the bigger problem, in fact, is that this point and this point on the ground, they appear at the same location in the radar image. So you have a mix of points in your image. Not really a problem we can solve. We can be aware of that. You can solve it using many images and a lot of smart processing. But in principle, it's a fundamental problem. I used to think this was very bad because I thought, oh, we have these issues. But that's because we don't realize that in optical images, we have the same kind of stuff. So we also have a projection, it's a different projection, and the optical projection is also a pain. And the only thing is that we are used to it. So if you watch a TV with an angle, everything looks very, very bad. But we are used to compensate with our brain, so it's not a big deal. So these are distortions of the image. It's a projection, not a big deal, but you have to be aware of that. And then we have shadowing. Now, these geometric effects, they play a role in your choice of angle of incidence. So what angle you choose, so if you go to very steep angles, then you get more signal back, but you get much more of this distortion. If you go to large angles of incidence, then some things are better. More shadow, so that's bad, but it is what it is. Okay, I gave you that. The resolution is slant. The resolution on the ground is going to be the same as we had in slant, divided by the angle of by the local angle of incidence, or the sine of the local angle of incidence is what you were showing before. And I'm going to just illustrate the effect on a nice image. Some examples here. What you're seeing is what we did a bit in history. In Europe, we started with the ERS1, ERS2, followed with MVSAT. And back then, we were very happy that we had 60 megahertz available, and that gave us a resolution in range on the ground of about 20 meters, which is not great, but back then it was great. The reason to limit this to 60 megahertz was technology. We could not generate enough power to have a larger bandwidth is over there, or there, with enough quality in the image. So there was a purely engineering limitation. We could not go, and you can see that if you go to our current European C-band satellites, We have increased the resolution by a factor of 4 because we can afford a larger bandwidth, because we know how to make better amplifiers on board, better antennas, generate more solar power. So this is an engineering limit. At some point, we will hit the legal limit, but the legal limit is still far away. We can go to 200 megahertz, so we can improve the resolution still by a factor of 4 before we start fighting the communications people. So there is space, but at some points we would hit the limit. People liking high resolution imagery, so this is many people in the civil sector, but also a lot of people in the non-civil sector who like to actually see stuff in detail. They want more bandwidth, and they typically go to higher frequencies. So they go to X-band. At X-band, you have more bandwidth available, and it's also easier to build a high bandwidth system if the center frequency is high, because the difficulties from an engineering point of view are over related to the bandwidth relative to the center frequency. I added, in this slide, I used to only have these three. I added biomass because it was launched, and biomass is very bad in terms of resolution, 50 meters in range, and then you have to average, so you're very limited in what you can do with it. And that comes because of the bandwidth, and this is what was available. And that makes sense because actually 6 megahertz is quite a lot if you consider that the center frequency is 450. So if you take it relative to the center frequency, it's quite good. So if you scale it up to, if you go 10 times, then you would be at 60. So it's comparable in relative terms to what you have for Sentinel-1. Now, is it a problem that the resolution is bad? Not really, because it depends on what you want to do with it. And if you're trying to map, inventorize global biomass and centering the rainforest, you are not interested in images of 5-meter resolution. We are looking at plots with 200 meters is fine to do what you want to do. And that's always an important thing when you're designing a mission. What resolution do you want? If you don't think about it, you're always going to say as high as possible. But if you start from the application, then you can often see that you can be fine with 100 meters, or you can be fine with 50 meters, maybe 10 is fine. So it always depends on the application. Now, we have seen the distortions, and now I give you a nice high resolution SAR image. This is an X-band, TerraSAR X, one of the German satellites. Quite cool. And the question for you would be, can you recognize what would be the range dimension? It's a two-dimensional image. And would you say that the range dimension is vertical? So is the radar looking from up, from down, from left, or from right? That would be the question. So who thinks we are looking at the image from the right or from the left? Nobody. Who thinks we are looking from the top and from the bottom? Okay. It's nice that nobody thought left, right. The right answer is from the top. So the satellite will be flying either from left to right or from right to left. Now, in fact, from left to right in this case, and looking to the right. Most SAR systems look to the right. This has to do with the position of the sun and things like this. But what you see here, as an example, is you see how the slopes are compressed in. So one side of the slope looks compressed and bright, and the other side of the slope looks actually better without zooming in. So one side of the slope looks compressed, the other one looks longer, and this is this foreshortening effect. And the fact that you see more signal on some brighter signal on one side than the other is half because of the slope. So if you face the radar, more of the signal will bounce back. But most of it is actually because there is a bigger pixel. There is a bigger area in the image because of the loss of resolution. So if you have 20-meter resolution because of the angle of incidence instead of 2, then you will have 10 times more stuff in the pixel reflecting, which will lead to a higher signal. So that's most of what you see over here. As you can see everywhere, slopes facing the radar look shorter and brighter, and the other sides look longer and less bright. Another example, in this case, we are flying like this, looking to the right, and this should be more or less circular, but one side of there's this big mine in Chile. I think if I click, you can see what it is. This big mine should be more or less symmetric, but one side looks totally compressed, whereas the other side looks totally not compressed. And this is because of the imaging geometry.
Paco, so these images have to be geometrically corrected completely, or
If you are not really a true radar person, for sure that's the first thing you do. And the question is when. So if you are developing a processing chain, you try, or at least we try, to do everything in radar geometry, and at the end, when we are done, we geocode it, and then everything goes to the right place.
Okay.
Yeah. But yeah, you have to. But this is also true for optical images. You also have to, yeah. Okay. The other thing that I think is important to realize is that because we can penetrate through things, so if you are looking at a hard surface, then it doesn't matter. So you can put everything on the ground, it is clear. But the moment you have multiple targets contributing to a pixel at different heights, this can be because of this layover effect. It can be the tip of the Eiffel Tower with something which is on the ground closer to the radar, but it can also be the canopy in a biomass image, or it can be the layers of ice when I'm looking at Greenland or Antarctica. You have an integration of a 3D world into a 2D image. In an optical image, that doesn't really happen because you are only seeing the first thing the sun sees when it hits the surface. But in a radar, you're always integrating. So it's always a projection of 3D into a 2D, so it's a mapping. And often you don't care, but you should be aware of that. So there's potential for contributions from different places or from different depths contributing to this pixel in your image. So that's one thing. Okay. And the other thing that you should be aware is that who likes complex numbers? And who dislikes complex numbers? Right. And this is a failure in the educational system. So we should convince everybody that all numbers are complex, and you just happen to work mostly with numbers, complex numbers with zero imaginary part. If we did this consistently at high school, then everybody would like them. It's just a matter of getting used to. If you work with radar data, then you should embrace complex numbers, because the images we generate are complex numbers. And they have a real part, an imaginary part. You typically prefer to look at them as having a magnitude and a phase. For many applications, you only care about the amplitude. For many other applications, you care about both. The amplitude tells you about how much signal reflects back. Obviously, the phase is telling you something about the object. And if the object changes, the phase will change. But the most important information it carries is it carries information about the position of the target. And phase has to do with the distance, but it's wrapped by the wavelength divided by 2. So when the phase changes, you can interpret that as a change of position of the target. You cannot measure absolute position with the phase, but you can measure changes of position incredibly accurately. And with time series of SAR systems, we managed to measure deformations as small as millimeters per year, which is great for many applications. We can do that because of the phase of that complex number. So dealing with complex numbers is actually good, but you have to like them first. And you get to like them if you work with radar. The amplitude of an image or the power, the intensity is given by the radar cross-section. If you were not doing imaging radar, then you would really look at the RCS, the radar cross-section, and you can have numbers. So insects are small, humans are about 1 meter square in terms of radar cross-section, and a big airplane is big. The size of the object does not tell you directly the radar cross-section. If you put a gigantic smooth metal plate on the ground and you look at it with a radar, you will get nothing. And the reason why you will get nothing is because the signal is going to bounce on the metal plane away from your radar. So nothing goes back. So the physical size is not an indicator of how much you get back, but if you have no physical size, you will also not get something back. Okay? But there are things which are very bright and small, and there are things which are very big and not bright. So it's not a measurement of size, it's a measurement of something else. We have what we would call it radar cross-section. For imaging systems, we want to normalize it somehow. And we divide the radar cross-section by the size of the pixel. There are different normalizations, but we always try to normalize by size of the pixel, such that we can compare different images with each other. So you can compare images acquired by sensors with different resolution. In terms of this normalized radar cross-section, they should give you the same value. So that's a nice way of normalizing things. There are other normalizations which I will not discuss. In general, for most areas, the amount of signal we get back depends on the roughness of the surface. Rougher surfaces will give you more signal. Smoother surfaces will give you less signal. If you have stuff, if you have vegetation, trees, then you have a very rough surface, which will give you a lot of signal back. Human-made objects tend to be full of square angles, and square angles tend to produce very strong reflections. The same way we put these reflectors on a bike to be seen by cars. Those things are prismas, inverted prismas, and they have lots of square angles, and the square angles produce nice bounces. I have an example of a Sentinel-1 image time series, which I don't know if it's going to work. I guess it's not going to work. So it's fine. Okay. So this was super cool, but you're missing it. But if you have access to the PowerPoint in the folder, you can look at it in PowerPoint and you get a nice, cool animation. I have a slide on product levels because I guess not everybody is aware of product levels. We have product levels going from 0, 1, 2, 3, 4. I work on the development of SAR missions, which means that I don't care beyond 2. And many users never look high, so lower than 3 or 4. For radar, level 0 is the raw data acquired by the satellite, and you never look at it. So you as a user are never going to look at that because you have to be really a nerd to be able to identify anything in the raw data of the image. In this example, there is an example. I can actually see a very strong target over there. It looks like somebody dropped something in the water. And so I could identify at least one target, or maybe 2 targets, but that's about it. So there is no information there. You first need to process it and image it. If you want to know something cool, what you see on the top is actually an hologram. So it's a hologram, and then you can convert the hologram into an image by doing something cool, which is our processing. The first level of data that you as a potential user would be interested in is the level 1, typically A, which are the single look complex. Now, the people not liking complex numbers will skip to the next one. But it is the first useful product coming out of a SAR system. And then we can start averaging, and then I would call level 1B. These are all engineering products. At the end, what you want is a level 2 product with your physical meaning, or a level 3 product where you combine different images, or maybe different sensors, or maybe a level 4 where you start including models and everything to get a super cool product using all these nice AI techniques that you're learning about. The thing I wanted to show, and I have a slide about that later, and I will hopefully get to it, is that the single look complex image, I'm not showing the complex numbers here. I would need two images to show you imaginary part, real part, or something like that. I'm showing the intensity, but it looks very grainy. It looks very noisy. And this is not a bad sensor. This is a good sensor. And the fact that I see this graininess is what we call speckle. This is inherent to the measurement. And this is the reason why we need to spatially average. So when we go from here to here, what we are doing is averaging. And the higher resolution you start with, the more you can average to get a nice looking image that you can interpret. Okay, so, and that's why when we talk about the resolution, if you buy a SAR system, they're going to tell you, resolution is 1 by 1 meter, but you get this. And you don't want this, so you want to get this. So when you specify a system, you go from what resolution do you want to have your end product at, and then you have to work your way back towards the original image, knowing how much you need to average, and then you can go back and do your things. Okay, a bit of product levels. Now, we have the range resolution, and I think that makes sense. The parameter that matters is the bandwidth that we have available. Now, let's try to explain how things work in the other dimension. This is super fundamental, and if you don't know, then I hope if you can learn something in these next 2 slides, then my day will be good. If you have any system that applies to optical systems as well, where resolution is angular in nature, and that's the case for radars in the direction of flight or in the direction orthogonal to range. The resolution is going to be given by, let me click so that it appears. Okay, the angular resolution is going to be given by this expression, super fundamental. So if you follow space telescopes, and when they did the James Webb Space Telescope, they had to build a big one. And the reason why they need a big telescope is this one, because they want to look at small stars far, far away and separate them. So they want to have very fine angular resolution. In that case, the wavelength was not very small because they're in the infrared. So it's very small for me, but it's not very small in absolute terms. And to get a very high angular resolution to distinguish objects, you need a very small ratio of the wavelength to the size of your aperture. And this is true for any observing system, also for an optical system. And this is the reason why you can make very small optical cameras, but your thermal infrared cameras, which have a wavelength a few orders of magnitude larger, become bigger. And you need a bit of a telescope to actually make a thermal image, because your wavelength grows, therefore your aperture starts growing to the point that it becomes complicated. Now, for us, we have wavelengths that go from centimeters to maybe a half a meter or something like this. So this ratio, keeping it small, becomes very hard. And now, if you want to translate that to a range resolution, then you multiply by the distance, and then you can do numbers in your head. So a satellite typically flies at between 500 kilometers and 800 kilometers. You look to the side. So the targets are at about 1 million meters. So put 1 million over here, put here 10 centimeters, 0.1, so it's still 100,000. And now try to get your antenna length to get here a resolution of meters, right? So you're going to need many kilometers of antenna, and that's not going to work, right? So we cannot build kilometer-long antennas in space, and that's the entire key of synthetic aperture radar. So you cannot do this. Yeah, so to have high resolution, you want to have a long antenna, but it's not going to work. With the numbers that we have here, this is not going to work. So the little trick is fantastic when this animates. It's not fantastic like this, but it's fine. So now you imagine that I start with only this, and then you see this, and then slowly I make the other ones appear by a nice animation, but this saves some time. So what we are doing in a SAR system is I'm going to be here, I'm going to make an image of you. You will all be scrambled because I don't have enough antenna to separate. My eyes can, but my antenna cannot separate he there from he over there, because they all look together in this direction. In range, I'm fine because I have a very high bandwidth, but in this direction, we are all mixed together. But what I'm going to do is I'm going to move, and I will do the same, and I will move, I will do the same, I will move, and I will do the same, and I will benefit from the fact that you are not moving, and then I will process everything together to synthesize a very long antenna. And that's what synthetic aperture radar means. So you synthesize a very long antenna from a small antenna that is moving. And that's the entire idea. And it works very well, but not always. Okay, so you synthesize, and then you end up with this very short antenna. And now these are equations that you can read by yourself in the PDF in the folder that I think you should have access to. But the end result is the thing that everybody was learned about SAR learned at some point, and that is the azimuth resolution. And then you get a very nice paradox. The azimuth resolution of a SAR system, if you don't do anything fancy, which we actually do, but the fundamental resolution that you can achieve with a SAR system is the antenna length divided by 2. And this is a very nice paradox. There's one thing which is good. Range is gone. With an optical system, or if you try to build a telescope, then the farther you want to look, the bigger you need to make your antenna. For a SAR system, you don't care. The distance goes away. And the other cool thing is that we started with, I want a large antenna to have high resolution, but now I'm in the opposite world. A small antenna is going to give me a higher resolution. And that's easy to understand because if I start with a small antenna, then I start with very bad resolution. So it means that I'm seeing a very wide angle. And that means that when I start moving, things remain inside for a long time. So the wider my starting angle, the longer I can look at stuff. And that means that I can build a very long aperture. So my synthetic antenna becomes longer when my antenna starts being short. So high resolution systems, short antennas, lower resolution systems, long antennas, which is the opposite to the starting point of you want a large antenna to have high resolution. I'm going to make this get quickly. I hope this works. Now, this is of course not working. Okay. Good. Then I have to do it without this. Let me see. Okay. So this would be a great slide if it worked, but it's much better when you look at me and instead of the slides. There is a nice way of understanding how I can achieve resolution. Very intuitive, and it explains lots of things. If I'm moving in this direction, then I'm getting closer to the people on that part of the room, and I'm moving away from the people on that side. So I'm moving in this direction, and I'm approaching you. If I were to sing in a very pure tone, then what I sing would be Doppler shifted. So the people over there would hear a higher frequency. The people over there would hear a lower frequency. Now the radar is singing. It's transmitting a signal, receiving the echoes. The echoes get Doppler shifted. So from that side, they have a positive Doppler shift. From that side, they have a negative Doppler shift. And that allows me to discriminate. So I'm seeing signals coming back with different Dopplers. The Doppler tells me from what direction the signals are coming back. To measure this Doppler, I need to transmit many pulses, compare them with each other. So it's not trivial, but that's the fundamental thing that you can have in your head. There is one way of understanding star imaging, but it's a nice way because it explains many things. And so I have range, and I have this Doppler space, and each target has a range and a Doppler, and this allows me to do. Imaging is a bit complicated, but it goes like this. And this brings me to this super nice slide. This is a super nice image for many reasons. This was the first image acquired by TerraSRX when they launched it. And the people at DLR are great. So they managed to very quickly after launch have the first image, and they process and it works, because that's what Germans can do. They do something and it works at once. And this was the first image. And we always advertise SAR images as we are weather independent, blah, blah, blah. And this is very nice because the first image shows you that's not really true. So you have, everybody can see clouds over here. So if you can see the clouds, so probably a lot of rain back then, X-band, short wavelength. So if it rains enough, you're going to see it. So I like this because we keep saying we are weather independent. It's not really true. Sometimes we see weather. But the other cool thing is that there is a train line in the image, and by chance there was a train going and you can see it over here. And you see the track of the train, and then you see that the stupid train is not on the track, right? And now, hypothesis one is that this was a Russian train, so maybe they're not that good, and they get off the line. Hypothesis two is that it's an imaging artifact, which you can understand very easily now, because I know that I put things on the image based on their distance and their Doppler. Now the train is moving, and it has its own Doppler, but I don't know. So when I image, I look at the Doppler, and I think that thing is over there. The moment something moves, it adds an additional Doppler to the image, putting the target in the wrong place. This is what we call the train of the track effect because of this effect. And it tells you a lot. So it tells you that if things move, they appear in the wrong location. It's not too bad because you can still recognize the train. If you are very smart, then you can actually estimate the speed of the train, so that's cool. But it tells you something more fundamental. SAR images assume that, or SAR imaging assumes that things are not changing while you image them. The train is changing its position, it appears in the wrong location. Things moving while being imaged by a SAR system are going to appear not only at the wrong location, but maybe they will appear defocused. I like looking at the oceans with SAR systems. In principle, you cannot make an image of the ocean with a SAR system because the ocean decorrelates extremely quickly. Now, can you do something? Yes, because it doesn't decorrelate instantaneously. But when people tell you, I have a system with 1 meter resolution, I'm going to image the ocean, that's not true. They're going to get lots of nice independent samples. They can average a lot, but the achievable resolution is going to be limited not by the equations that I have over there, but by the correlation time, the coherence time of the ocean surface, as seen by a radar, which is in the order of, depending on the wavelength, 10, 50, 100 milliseconds, but it's quite short. But that's something to understand. So things work very well as long as the surface is not doing anything, as the targets are not moving, not decorrelating, which is most of stuff. So most of stuff stays put for a few seconds, enough to make a nice image. But there are things which do not. Okay, I will skip these slides until giving you something meaningful. In range, I told you that the resolution is given by the bandwidth of the pulse. If I now try to, and in the flight direction, I told you this nice equation. So the resolution is going to be antenna length divided by 2, easy to remember. I think it's also beautiful to relate it to the Doppler bandwidth, because if I look at a target, if I follow a target, first it will have a positive Doppler when I'm approaching the target, and at some point it will have 0 Doppler, and if I continue, it will have a negative Doppler. So there is a variation of the Doppler while I look at the image. And since the Doppler varies, I can talk about the Doppler bandwidth, the change, the excursion of the Doppler during the time I see the target. So I can put the different Dopplers that I see at different points, and things are a bit out of location. But let me go to the one I like. So let's just, you can follow the equations by yourself in your free time, but this is the one I like. So we had the range resolution, which was the speed of light divided by 2 because of the two-way divided by the pulse bandwidth, very fundamental relation. And now we find actually the same expression in the other dimension, but instead of the speed of light, we have the speed of the satellite on the ground, the projection of the speed of the satellite on the ground. And then we have something which is the Doppler bandwidth that we have. Small antennas, large Doppler bandwidth. But I like this expression because it's similar to the other one. It's speed divided by a bandwidth. And then if you put units, then it makes sense too. And then let me write it the way I like it. If you look at the specifications of a system, then what you find is the process Doppler bandwidth. If you ever look at the specs of Sentinel-1 image or of whatever sensor of choice, then if you look at the metadata, there is somewhere a parameter which is the process Doppler bandwidth. That's a bit of a choice because depending on how you process, you get something which is so more process bandwidth, higher resolution, but then you have other problems. So there is a parameter and which you can control. So if you want to understand the resolution of a SAR system, and by looking at the metadata, then you need to know the velocity of the satellite, which is about 7.5 kilometers per second in space, but on the ground is a bit less than 7 kilometers per second. And then you divide it by the process bandwidth, and that gives you the resolution of the system before averaging. Resolution matters, yes. Can you see anything? Yeah, you're so good. All right, most people cannot. And high resolution, then you see the pyramids, but only because we average a lot. Yeah? So the trick here is not only that the resolution was higher, but also that because we had higher resolution, we could average a lot, and you could see the pyramids from the opposite side. So in this case, we look from the left, now we look from the right. And if you think this is very bad, you have to realize that when people were operating the system, they were extremely happy with that. And that's because they were not interested in the pyramids. They were interested in other things. So if you look at big things, then this is fine. But if you want to look at a pyramid, then it's not good, right? But resolution, of course, matters. And now I go back to my images. I showed you these ones before. This is the single look image of an airport and some airplanes. Super hard to interpret. Not for the AI people, they just throw AI and they do. But in fact, if you throw AI at this, what AI is going to learn is how to somehow first do this and then interpret it in a clever way. But here you see much more detail. The screen is not great now, but you see things, but there's less salt and pepper in the image. and only because we average. So the difference between left and right is averaging, and then you can call it with fancy names, and you can do it in very, very interesting ways and write PhDs about that. But in the end, better image means that you average more. And the interesting thing to do when you are doing this is that if I'm averaging, I do not want to mix the forest with the grass, and I don't want to mix the landing strip with the grass next to it or the buildings. I only want to average things that are sort of the same. So you can play all kinds of games to adaptive filtering, or nowadays we throw AI at that to do it in a nice way. But it's all about averaging pixels together that you can average together. Then a bit of a theoretical toolkit for you. If I take an SLC image of an homogeneous area, then what I get is something which is random, and the only thing that I have a complex number with real and imaginary part. Both numbers are Gaussian, so I have a circular Gaussian complex random variable, and so I cannot do much with it. If I look at the amplitude, then we have what we call the Rayleigh distribution, which is a very wide distribution. So I'm interested in the mean. So I'm interested in whatever the mean is, but you can see that I have a huge spread. And this is the general shape. So this is the general distribution of any distributed target. So if I'm looking at a forest or a piece of grass or a landing strip, I'm always going to have the same distribution. The only thing that changes is the amplitude, so the A. But in relative terms, it's always going to be like this. If I look at intensity, so if I take the amplitude, square it, and that's what you want to do, then I have an exponential distribution. And in an exponential distribution, the standard deviation is as large as the mean. So it's very bad. So if you have more signal, then the variation scales. So that's why we call this speckle, we call it multiplicative noise, because it scales with the signal itself. So you cannot beat it by having a better target. You only beat it by averaging. So there is a very big problem, and this is the reason why we need to average, and that's why the resolution that we have is not the resolution that you think you have. Now, what do? You start averaging. If you have one pixel, then you get this Gaussian distribution. If you look at the amplitude, then you start with a Rayleigh. If you look at the power and intensity on the right, you have an exponential. If you average enough by the law of large numbers, everything starts becoming Gaussian, and the variance starts going down by a factor equal to the number of samples that you average. So you need to average. That's the message I want to put here. You need to average if you want to do most things that you want to do. Okay, now we have 3 minutes for a bit of imaging performance. I think I have the most important things that I wanted to tell you in there, but I have a bit of imaging performance. Something I care about is the noise equivalent sigma 0, which is the intensity, the normalized cross-section of the surface or of my target that will give me a signal equal to the noise in the system. And because if I'm below the noise, then I will not see anything. I will just see noise. So I want to beat the noise. There are things you can do by averaging, but you get a complicated expression. You don't need to look at it. But what's important is from a fundamental point of view, if you ever go to complain to ESA about the quality of the images, you should know what it takes to make better ones. And so if you want to make nice images, the first thing you need is power. And power is, since we cannot carry nuclear plants and things like this, we need big solar panels. So if you want a lot of power, then you need to deploy big solar panels, put heavy batteries, and that's what you have to do. So the quality of the image is constrained in the end by the size of the solar panels you can put on a satellite, which is limited. Something that helps, larger antennas. So if you have a bigger antenna, you collect more signal back, so it's going to work. Unfortunately, if I want to have high resolution, I don't like large antennas. So I have a trade-off between resolution, which likes small antennas, and quality of the image, which likes large antennas. You cannot have both. You cannot have super high resolution and super large antennas. So if you have a small antenna, then you need more power. But these are fundamental things. You can improve the quality in terms of noise by reducing the resolution. So low resolution will yield a better image, but then you cannot look at high resolution stuff. You can try to fly closer. The farther away, the less signal comes back. So if you fly closer, you can try. You cannot really fly below 500 kilometers, so that's a bit the limit. And then you have other problems. And there is a bit of hardware, there's a bit of engineering, but it's very limited. So there is some engineering factors that degrade the quality, but not much. You can at most make things twice as good, and then you're done. There's nothing more you can do. And then I tried to introduce two things, ambiguities. And there is a nice animation, which is actually working, which is great, by my old boss at DLR, which is very smart. And you see what's happening in a radar. The radar is transmitting pulses, and the pulses are hitting targets on the surface, and then you get signal coming back. And in this drawing, what you see is that, in principle, the different targets should give you echoes that arrive at different times. But since I need to transmit pulses one after each other, because I'm moving, and by the time I move a bit, I need to transmit the next pulse to synthesize my aperture, what happens is that there are targets on the ground which produce echoes, which, although they come from different distances and they have different delays, when they travel back, they align. So they align with the echo from the previous pulse, or they align with the echo from the next pulse. And when you are in space, there are what we call traveling pulses. So you do not wait for the echo to come back. You transmit, and then you receive the echo from 10 pulses ago, and then you transmit again, and then you receive the echo from many pulses ago. So there are many traveling pulses, and they all align. And that means that, in principle, I'm mixing the tree with the houses, right? And so that's an issue, generates ambiguities, and I need to solve that. The way to solve it is by having an antenna that discriminates, that only looks at the tree, and which is what's happening over here. The problem is that antennas are never perfect, so there is always a bit of tree on top of my house. And then I'm almost done before people start to kick me out of the podium. Now, the size of the image is at the end limited by the pulse repetition frequency, because otherwise things start to mix. The antenna needs to deal with the mixing. I will skip this one. I will show you the effect. This is an image that we managed to do at DLR when I had a group there, so I could tell people what to do. And I once told people to do something very stupid. And we produced this. And this is water, and these are mountains. And what you see is mountains in the water, right? And this is an ambiguity. And what I'm seeing is land which is ambiguously imaged on the water. And this happened because we made a very poor choice of this pulse repetition frequency, so we did everything wrong, but it produced this very nice pedagogic example of ambiguities. And they're always there. Most of the cases, you don't see them because they're small enough that you don't see them, but they're always there. They're always contaminating your images, always. So it's a fundamental limitation of your image. So this was the example. I want to show you one last thing, which is, I will not explain this one, but in the other dimension, we have the same problem. We have ambiguities in the flight direction for the same reason. It's a sampling problem. So I have an antenna. The antenna has a certain beam width, but the antenna has side lobes. So if I look at the different Dopplers, there is also some guy in the other room producing a very high Doppler. And to do this very right from a signal processing point of view, that would mean that I would need to have a very high pulse repetition frequency to be compliant with Nyquist theorem, which is something that engineers learn about. But I cannot, because if I have a very high pulse repetition frequency, then I have lots of problems with the range ambiguities, and it limits the swath. So I want to find something that works. And the result is something that doesn't really work, and I get ambiguities like this. So I'm flying in this direction, and these are containers, and then I see the containers replicated in the water again, and these are ambiguities. So I'm going to wrap up with the slides, which you can find yourself. Examples: ships appearing ambiguous. You see a ship and the ambiguities over there. You see also the nice ambiguities of the land. So ambiguities are everywhere, but most of the time we don't see them. And yeah, I have 2 slides to recap. Fundamental limits to the design of a SAR mission. The fact that I cannot miniaturize. I need a big antenna to collect enough energy. I need big solar panels. I cannot be a very clever engineer and make everything small. Physics limit me. So big, heavy, lot of volume, requiring a lot of power, You need batteries because sometimes you have no sun on your solar panels, so you need batteries. A lot of power requires large batteries. Something that people never think about is radars produce huge data volumes. And in most mission design exercises that I've been involved in, including my charming Harmony satellites, getting the data off the satellite ends up being one of the biggest problems. And so we are limited in how much data we can acquire by the fact that we acquire too much data. And then you need to get the data from the satellite back to the ground. Huge problem. So you could do the numbers yourself. And this is my, skip this one. This is my summary slide on the different parameters that are involved: range resolution, azimuth resolution, the sensitivity, the timing, the pulse repetition frequency, which leaks into the ambiguities, and you have to find something, limits the size of the antenna. We have a conflict there. If I design a system, I like to have a short antenna because it gives me high resolution, but I like to have a large antenna because it's good for sensitivity. I like at the same time to have very high pulse repetition frequency and a very low pulse repetition frequency. So it's always a trade-off, and it's very hard to find the thing that gives you the best performance. And that's it.